Okay, so first of all, let me introduce who is presenting today. Okay, so there will be presentations coming from Caroline Lurie, also from Sabina, from WindEurope, from Wei He, from Equinor. I think that she's the only one that really does not have the webcam, and she will be connecting by phone. Okay, then myself, José Luis Domínguez. Okay, also will be Rubén Duran from Cobra, and also Henrik from DTU. Okay. So the agenda, as I said, the key ideas will be to give you a brief overview on the policy of the context of offshore wind, then make really a short introduction to the COREWIND project, then explains you the 15 megawatts model, okay, that is quite specific for floating wind, and then also some couplet and integrated analysis for the mooring and dynamic cables, and finally some experiences, okay, for cost reduction of floating wind by Cobra and Equinor. Okay, so and at the end you will have some questions and answers section. Okay, so something that it's important to remind you, okay, is that if you want to make any question, please go to the questions box there and write it down. Okay, so we will try to answer as much questions as possible during the part. Okay, so and then the first presentation will come from Sabina. Sabina, your turn.
Can you hear can you see my screen?
Yes.
Great. Thank you very much, Jose, for your introduction. So in the next 5 minutes, I'll be telling you a little bit about the European policy context for offshore wind today, and notably the European Green Deal as well. But starting from where we are with offshore wind today. So as you can see from this slide, at the moment we have 22 gigawatts of offshore wind installed, which amounts to around 2% of Europe's electricity demand. So in this map, you see the gigawatts installed per country, which corresponds to the blue bars, and the wind share of electricity demand, which is marked in red. So today, the biggest markets for offshore in Europe, as you can see here, are the UK, Germany, Denmark, Belgium, Portugal, Spain, and also the Netherlands. But if we want to look more granularly in this 22 gigawatts figure to see what the share of floating offshore wind is, then we see that floating offshore wind amounts to 45 megawatts online today. So in this map, you see the status of floating wind projects today. So the red dots tell us which projects are online, so the 45 megawatts which I just mentioned. The orange dots tell us which projects are under construction, and the yellow ones tell us which projects have the permits to build. So I won't list all of the floating offshore wind projects online now, but I will just give you a few examples. So we have the Hywind demo project of the coast in Norway with 2.3 megawatts, the FloatGen project in France with 2 megawatts, and the Kincardine in Scotland with 2 megawatts. But if you want to see how the floating sector and the offshore sector will develop in the future, we should start by looking at the European Green Deal, which is, as you probably many of you have heard about it, this is the ambition of the new European Commission to at least halve EU GHG emissions by 2030, and then to reach net zero by 2050. So this is the European Green Deal is the European ambition, is the response to today's climate crisis. And here we have obviously a twofold challenge, because on the one hand, the Commission wants to accelerate the transition to renewables in the power sector by phasing out fossil fuels, or starting to phase out fossil fuels already by 2030 with higher renewable energy targets. And secondly, also to phase out fossil fuel in industry, transport and heating through both direct and indirect electrification. But how will all of this essentially function and concretely be translated at national level? This will be done by the 2030 National Energy and Climate Plans, which are basically those documents that outline how different European member states will translate those objectives in their own country. And we're very happy to know that, for example, France has submitted their final NECP recently with very high ambitions also for floating. So they say that they will want to install 750 megawatts by 2022. So this is very positive. And also, obviously, to implement all of these objectives, the European Commission states in the European Green Deal that they will mobilize at least 1 trillion euros between public and private investments over the next decade. And obviously, within the European Green Deal, offshore wind occupies a very special place. But what does that mean concretely? So the vision for the European Green Deal is to have 450 gigawatts of offshore wind across Europe. And between 100 and 150 gigawatts will be floating. So almost 1/3 of that figure will be floating offshore wind. And we expect, as you can see in this map, that 85% of this capacity will be developed in the North Seas, and another 70 gigawatts will be developed in southern European waters. So the industry is expecting that markets like Portugal, Spain, France, Ireland, and Scotland will progress earlier on floating offshore wind technology. So why is floating offshore wind so important, and how will it help us in achieving that 450 gigawatts that I just mentioned? So the answer is quite simple. Essentially, 80% of all the offshore wind resources are located in waters 60 meters and deeper, where you can put floating and where bottom fixed offshore wind is not economically attractive. So in this slide, in this map here, this 80% that I just mentioned corresponds to all the green, yellow, and blue areas, whereas only the red areas are suitable for bottom fixed offshore wind. So basically, floating offshore wind has the potential to further increase offshore wind power capacity. This is the essential point. But also, floating is important for another two reasons. First of all, it allows for larger wind turbines, so between 12 and 15 megawatts, to be installed. And second of all, floating offshore wind will also help speed up technological development, because it will allow for more overlapping research. So in turbines, in cables, interconnections, etc. And this is what we are doing, for example, with the COREWIND project. But another important point is how do you develop that supportive policy environment to reach those 450 gigawatts and to support, obviously, also floating wind. And this is something that the European Commission is doing with their offshore renewable energy strategy, which is planned for October this year. And there are several key elements within this strategy. Some of them are, for example, a regional approach to maritime spatial planning, happy coexistence also with other actors at sea, so for example fisheries, grid development, both offshore and offshore, and finally also commercialization and industrialization of floating offshore wind. So we're very happy about this, and if you have any questions, just let me know through the question box, and I leave the floor to you, Jose. Thank you.
Yeah. Okay, thank you so much, Sabina. Now let's move to the presentation about just a brief introduction to COREWIND project. See, I think I put the wrong one. Okay. Everyone can see it?
Yes.
Good. So
Yes.
it will be really a short introduction just to the project, just to let the people know what we are doing and what we're expecting, okay, for the COREWIND project. So first of all, let me introduce what partners are involved in COREWIND project. Okay, we believe that within the consortium, we are covering the whole value chain, okay, from research till developers and owners and so on. So we have like covering the whole spectra. We have like lots of partners like Equinor, DTU, UL, GTR, INOC, HR Cantabria, Cobra, UPC, Politecnico de Milano, Stuttgart and Ramboll, and of course IREC. Also, we have some third parties related to the project as the University of Cantabria, STEICO and UL OCC. And also we have some advisory board that also help us on leading the key lines and drawing the line somehow of the project as NREL, DIM, IET, InnoEnergy, Carbon Trust, and WindC. Okay, so which is the key objective of that project. Okay, so at the end we are trying to go beyond the state of the art for floating wind, developing and validating innovative solutions. Okay, mainly focused on the part of the keeping parts. So we are having the mooring, the anchors, also the power transmission cables, and also some of the operation and maintenance part. Okay, so we are trying to go deep on that advances. And the key objective of the project is not only to reduce the current cost of the floating wind, but also have to speed up that cost reduction. So we are foreseeing that thanks to our innovations, the objective of 80 euros per megawatt hour will be reached 10 years earlier than expected. Okay, how we are planning to do that? Okay, so we will take advantage of some LCOE and LCA tools for the cost assessment and the environmental impact assessment. Also, we will take advantage of digitalization, so we will develop digital twins, BIM toolbox, and also we will optimize the mooring and dynamic cables as you will see later, okay, in some of the parts. And finally, we will go to lab to test, okay, so there are some hardware in the loop testing with a wave tank and wind channel, okay, for testing all that developments. So I think some of important parts of that is what we are expecting to deliver, okay? So not only we are aiming to reduce the cost, but also to provide some, let's say, helpful information for all the wind society and all the stakeholders. Okay, so we are working on the 15 megawatt wind turbine models that Henry will explain later. There will be a couple of floaters models also, semi-sub and Spark. It will be developed one toolbox for BIM specifically developed for floating wind industry. Then the digital twin will be quite focused on quite an agnostic one. So up to now has been quite specific for the developers. So we are planning to make one generic that can be used in general. And also will be some part of the OEM specific for floating, okay? And last but not least, please, I think that can be quite interesting if you want to join the conversation. So with us in Twitter and LinkedIn and so on. So with the /COREWIND, you can just follow the conversation, but also please follow us for all the updates and all the outcomes that we will be developing within the project on Twitter and LinkedIn in the following links, okay? So if you have any question from the project, please don't hesitate to ask me and we will answer later on. Also, then the next presentation will be given by Henrik, and it will be about the 15 megawatt wind turbine model.
Thank you very much. And can you see my screen now?
Yes.
Great. So thank you for this opportunity here to present the definition of the IEA 15 megawatt wind turbine and how we will use it in COREWIND. This turbine has been developed by NREL and DTU, and DTU's work has been part of the COREWIND project. And my name is Henrik Bredmose, and I'm from DTU Wind Energy. Wind turbines offshore, they are increasing in size. So here is the statistics from WindEurope with the annual average of the turbine capacity every year. And you can see this is now approaching 8 megawatts. So they are constantly growing. And when we do research, we have a need for turbines which we can study and look at and which can be freely shared. And that's where the role of these reference wind turbines come in. There is a history of reference wind turbines. So the most known ones is the NREL 5 megawatt turbine from 2009, the DTU 10 megawatt turbine from 2013, and now the next one is the IEA 15 megawatt turbine, which was announced in February this year, and which this talk is about. And the reason that we are interested in such a turbine in COREWIND is that we are looking at wind farms, mooring systems, and dynamic cables. And to make these studies realistic and relevant, of course, we would like to use a turbine which has a size which is relevant and points a little bit out in the future. And also, we need something to, say, create the loads and motions which are, say, the subject and the background for the design of these mooring systems and cables. So here it is, the 15 megawatt reference wind turbine. It's 240 meters in rotor diameter. It has a standard hop height of 150 meters. And there's a report here which details the design and gives all the specifications. I already mentioned that it has been made by NREL and DTU, and it's available at GitHub, both as fast and Hop2 models, freely for everybody to download. And we can go a little bit more into the specifications of the turbine. It's an IEA Class 1B turbine. It has collective bed pitch control. I already mentioned the 240 meter rotor diameter. And now as a new thing with respect to reference wind turbines, it's a direct drive turbine. So you can see here is a picture of the stator with all the coils and the whole assembly of the generator with stator and rotor and the hop out here and the bearings. It has a rated wind speed of 10.59 meters per second. In the specification document, there's also a comparison between the DTU 10 megawatt reference turbines and the new 15 megawatt turbine. And you can go down and compare different numbers. And one thing to notice is that, say, the maximum speed of the rotor is now 95 meters per second. So this is 5 meters per second more than we had originally at the 10 megawatt turbine. Still, it goes at a lower maximum RPM. It is 5 RPM at max, whereas the old one is 6 RPM. And that is due to the larger rotor diameter. So here you see how the size sort of influences the design, and the tip speed requirement then leads to a smaller rotational speed at maximum for this turbine. Another thing to look at is the top head mass. So here the rotor and nacelle assembly mass is just about 1,000 tons, which can be compared to the 674 tons of the 10 megawatt DTU turbine. The performance curves of the turbine are shown here. So in the upper plot, we have as function of wind speed, the blade pitch curve here, the tip speed ratio in yellow, and the generator torque as this red curve here. And if we go down, we have thrust and rated power. So rated power, 15 megawatt, achieved at 10.59 meters per second. And the thrust curve is shown here. And we can see that the maximum thrust is just above 2,500 kilonewton. So of course, this is a key piece of information if you want to design a substructure for this turbine. So now the use of this turbine in COREWIND. So in COREWIND, we have defined 5 reference sites. There's one west of Barra in Scotland. There's the Canary Islands, and there's the Morro Bay. West of Barra was also used in the last 50+ EU project. Now in COREWIND's design basis, which is an open document that can be found on the COREWIND website, we have wind wave conditions and joint probabilities for these 3 sites. That forms the basis for the design studies in COREWIND. So what we are doing now is that we are designing 2 floaters for those 3 sites. There's the active float semi-submersible floater designed by Cobra and Esteco. It's a concrete semi-sub with an active ballast system. It will be designed for all 3 sites. We also have the WindCrete spar design, a 15 megawatt concrete spar floater designed by UPC. That one goes for the 2 deep sites of the 3. And both designs will be made available as public fast models at the same GitHub as the reference wind turbine. And actually at that same GitHub site, there will also be a floater designed by University of Maine, which are also designing a semi-sub. So we are in good company at this site, which will be the central site for sharing of public floater models for this turbine. So with 2 floaters designed specifically in COREWIND for this new reference wind turbine, we are ready to go ahead in COREWIND. So now the use in COREWIND will be, say, as load and response drivers for mooring studies, for dynamic cable studies. We will make physical model tests, and we will also make studies of O&M, lifetime, and levelized cost of energy. And this is research in COREWIND that is ongoing in the next couple of years. And of course, we invite everybody to follow that, join us on the COREWIND site, and of course, see all the output, publications, etc. And this concludes my talk. Thanks very much for your attention.
Okay, thank you very much, Henrik. Now let's move to the presentation of Caroline about the integration and the integrated analysis of dynamic cables and mooring.
Hello, thanks very much, Henrik and Josie. So in this section, we will be looking at the benefits of coupled analysis and optimization strategies for floating offshore wind farms, looking at the mooring and the cable design systems. As part of the COREWIND project, which as we know is looking at cost reduction and innovation for floating offshore wind, the mooring and cable work packages will focus on cost optimization of the mooring and cable systems. These systems are closely interdependent, and the design limitations and cost related to one can significantly impact the other. So in this presentation, or this part of the presentation, we'll look at the design and cost drivers for moorings and cables, the mooring and cable design and configuration process, optimization of that process for the mooring and the cables, and opportunities for cost reductions on a commercial scale. Cables and moorings share many similar design and cost drivers. In this table here, the text in bold indicates where we have a high level of dependency on the parameters, for example, met ocean environmental conditions, water depth, and fatigue. The critical difference between the moorings and the cables is the excursion limit for the floater device, which is significant for the cable configuration and is defined by the mooring design. The size of the wind farm and economies of scale for commercial floating offshore wind farms in the future will be relevant, particularly for ancillaries and installation costs. Mooring configuration design considers the global response of the floater and integrates both the hydrodynamic loads on the structure with the aerodynamic loading, coupled for the turbine mounted on the structure. The complexity and the cost of the anchoring system will also be a significant driver in the mooring configuration. The environmental loading, how much the mooring lines will be loaded by the environment, marine growth, build-up and biofouling, and the water depth will also play a part. Compliance with standards and ensuring the integrity of the design are also quite critical. Some examples of some mooring philosophies at the bottom of the slide there. The catenary style will have longer chains, will have more impact to marine life, but does have lower anchor costs and results in larger horizontal movement, which may cause some difficulties for the cable, as we'll come on to shortly. Whereas a taut mooring system, which could use maybe synthetic fibres or wire, will typically be more costly, but will have lower impact to marine life as it has a lower footprint and has less seabed disruption. It does, though, have larger anchor costs as you have higher loads to withhold, and it does limit the horizontal movement, which has a more positive impact on the cable configuration. The main cost driver to the mooring design is the cost of the components of the mooring system. Mooring design process, just an overview here. Obviously, a creation of a design basis and a brief to determine the functional requirements for the mooring system, and go through iterations and checks to ensure that the designs are compliant with those functions. The dynamic load case definition and model creation then occurs, and iterative loops of the static configuration screenings, quasi-dynamic and frequency domain, extreme and accidental load state analysis, which consider the hydrodynamic and aerodynamic loadings on the platform, and time domain analysis, as well as fatigue analysis for operational and installational loading are also accounted for. And then the design can be finalized to specify the materials, the ancillary hardware requirements, connections, and so on, as well as the logistics, including transportation and installation. A similar process for the cable configuration, though here we start with the cable design, its electrical parameters, the current loading on the basis of the number of turbines for which each cable will be carrying current, the voltage of the system, and consideration of the electrical losses, the thermal losses, and optimization of the size of the cable on the ratings. Mechanical parameters that need to be considered for dynamic cables include torque balance, the tensile capacity for installation of these long lengths of cable in deeper waters, and resilience to bending loads. This will infer the material selection, as well as the requirements for design life and the cable's dynamic performance. Then to consider the dynamic configuration of that cable, we use Orcaflex software. Again, it's a complex trade-off, much as it is for the moorings, considering the complexity and variation within the site, critically the platform excursions, the water depth, again, environmental loading and marine growth on the cable, ensuring that we are compliant with the standards and checking the integrity of the design. The main cost driver to the cable configuration is the ancillary hardware costs, for example, buoyancy modules, bend stiffeners, requirements for tethers, holdback clamps and ballast. As for the mooring system, it's an iterative process whereby the dynamic length will be determined by the floater offset. and the dynamic length will be determined by the floater offset, with the positioning of the buoyancy to ensure that you have sufficient pliability within the system to avoid overtensioning. Determination of whether a tether is needed to avoid any touchdown point migration. We do extreme and accidental limit state analysis, as well as interference with adjacent lines and mooring lines, to ensure that the tensile and bending limits of the cable are not violated. Fatigue analysis over lifetime to ensure that there is adequate design resilience of the cable components. And we base this on best practice and experience from oil and gas and other floating offshore wind projects. And this then can confirm the cable design, the dynamic configuration, and the ancillary hardware costs associated. In COREWIND, the mooring optimization presented here, we have a generic fast Orcaflex model coupled Orcaflex coupled model, which includes moorings, floater, turbine, and all environmental loading conditions. We then have an eyesight model configured, set up with the initial values and boundaries of the mooring parameters, and then go through a process of optimization of the mooring line by eyesight, looking at the grade of material, the diameter length of the mooring line, size of buoyancy, clump weights, and so on. Fast Orcaflex simulations are then run to verify the design criteria, the line tension, anchor tension, offsets, and so on, and iterations for the mooring cost optimization, looking at the material and the installation costs. And in COREWIND, we will then have an interface from the mooring iterations to define the floater offsets, which will then be incorporated into the cable Orcaflex simulations. Cable systems, including all of the ancillary costs, can then be fed back into the overall mooring optimization to give a system level optimization. So to sort of summarize and look ahead, optimization of the mooring and cable system together means that we can reduce the overall system costs, but we need to be mindful that larger mooring offsets will typically increase the ancillary cost for the cables, and it will be influenced on a site-by-site basis and the requirements of individual projects. Considerations at the commercial scale, there are benefits to standardization of components, and there will be economies of scale as we move to the commercial size wind farms, and shared systems of anchoring and connection points will also offer opportunities. We imagine there will be a lot of innovations in materials and design philosophies for the cables and mooring systems. And looking ahead, we know there will be larger turbines. We will probably be looking at deeper waters, and these will all come with bigger challenges. We know, for example, there will be requirements for higher voltage dynamic cables, and we look forward to coming up with more and more innovative mooring and hardware solutions for these. I'll now hand over to Ruben and to Wei.
Okay, thank you so much, Caroline.
Thank you.
Now it's time for Ruben and Wei's presentation that they will give us some experiences on how to achieve cost reduction and implementing real floating wind technologies. Okay, Ruben, floor is yours.
Okay, good afternoon. It's a glad to present in this COREWIND webinar together with Wei. Thank you very much for joining. We will present by way to cost reduction in floating wind technology. Thanks to the experience gained in Kincardine and high wind projects. Okay. We would like to highlight several advantages that floating wind technology has against bottom fixed technologies. First of all, is the huge market potential. Why? Because of deeper water can be harnessed. These locations have extensive wind resources. The foundations are scalable, even up to the power of new wind turbines, roughly 15 or 20 megawatts in short term. Distance to shore reduce visual impact, and floating foundation allow to reduce environmental impact in the seabed as well. Okay. But research and innovation is still necessary to achieve the cost target rating between 40 and 60 euros per megawatt hour in 2030. Even though most of the audience know available types of structures, I could remark that three main technologies are now in place: semi-submersible, tension leg platform, and spar. According technologies developed in COREWIND project, we will explain semi-submersible and spar cost reductions. Okay, well, regarding cost reduction for semi-submersible technology, several are related to construction and installations, since full onshore manufacturing is possible, as well as installation doesn't require heavy lift crane capacity vessels. Furthermore, different stages can be executed in parallel, such as floating manufacturing, mooring, and cable installation. In this case, the figure shows the process from foundation manufacturing onshore, wind turbine assembly onshore, towing and installation at site, changing the drag during this process. Okay. COREWIND and new solutions such as active float use concrete as main material. Why? What is the reason? Because of bringing several cost reduction, respect durability, and serial production. In addition, local content is encouraged with these concrete solutions, which is a key point in many international tenders. Regarding O&M perspective, cost reduction brings mainly through minimizing offshore operations. To do that, it's important to improve accessibility during both landing and crew transfers. Plug-and-play strategies which allow to connect and disconnect easily mooring and cabling during the commissioning or major maintenance. Also, improving inspections with sensor remote operated vehicles or cameras is critical for reduce the offshore operation, as well as it's important the weather predictions to anticipate the accurate weather windows and predictive maintenance due to scarce available weather windows so far. Okay, now it's time to the turn of Wei. Okay, Wei seems it's not connected. Well, this is the pathway they have for high wind project from the prototype called high wind demo to the pilot park that they are developing now for giving energy sun offshore oil and gas stations to the end with a large park. This is the way that he has developed their spar concept. Okay. The starting point was 10 years ago with a successful operation. From September 2009, he started the installation of this high wind demo. All technical systems are working well. Concept was verified. This was the reason he goes to the High Wind Scotland pilot park in this slide we have some details of the project. Well, the project includes a 30 megawatts capacity and a battery and transmission voltage of 33 kilovolts, 5 units of 6 megawatts, and what the pilot park covers around 4 square kilometers. In this project, Kinor and Masdar invest around 200 millions, and the cost reduction achieved was around 60 to 70% against high wind demo experience. This is a view of the design, the layout of the plant that they use to provide energy to the oil and gas station. And well, thanks for your attention. Now, José Luis.
Okay, so thank you so much for that presentations. Now, following the agenda, it's time for the question and answers. We have already received some of those. Okay, so if it's fine, we will try to answer some of the questions that has been already made. Okay, there are some of them that are really directed to Henrik, let's say. So, first of all, they are asking about some issues with the 15 megawatt model. Okay, there are like 5 questions with quite related to the same. It's like they are having some problems with the current model of the GitHub, and they are asking when, if it will be uploaded or corrected, or if you also face that issues.
Yeah, I saw one saying we downloaded it in February and we have had problems with it. It has been updated since then, and I think, I believe the version which is there now is stable and runs as it should. There was also a question about, will it be with Windows compatible GitHub files? And I have colleagues that are taking down from GitHub in Windows, and it works for them. Then there was a question about the tower mass. So in that table I showed, there is a lower tower mass of the 15 megawatt turbine than for the old 10 megawatt turbine. And I actually looked through the 2 specification reports now, and in the 10 megawatt report, the tower mass is lower than what that table I showed states. So I will need to look into that. We might have a typo there. So thanks for bringing that to our attention.
Yeah. Then there are also some questions. I think that they are quite related to Caroline. Okay. Some of them are related to directly the dynamic cables and also on the optimization on that. Do you want to answer some of them, Caroline?
I can do, yes. So there's lots of questions coming in. I'm just trying to look at the interface here. So we, I think at the moment, looking at 66 kV cabling. I've been asked about the voltage that we're studying. I do, however, see that will be both for the array cables and for dynamic export cables at a commercial scale where we have floating substations. I imagine we will be moving towards higher voltages. And as José Luis talked about earlier, we have a kind of advisory board, including the Carbon Trust on the COREWIND project, and organisations such as the Carbon Trust are involved at the moment in accelerating technologies to support the aspirations of floating wind to the commercial scale, which includes higher voltage dynamic export cables. There was also a question about the use of lead. What I would say would be my opinion is that for static sections of export cables, with that being quite an established technology, that will likely still be used, but certainly with the developments that are ongoing, particularly for the dynamic export cables, I think we will be looking at other materials for those. Just skimming through the questions to see what else there was. Somebody had a question about whether this was relevant as well to floating solar offshore, and certainly from the mooring and cabling perspective, I think there will be a lot of synergy there. Yes.
Oh, and also there is quite a directed question to you, Caroline, from Stephen.
Let me just
From
find
yeah,
about the water
how
depth.
do you see this?
Oh,
How
no.
do you see the situation with lead becoming an EU substance of very concern?
Yeah, as I say, because lead is it is obviously a substance that we'll be I think we'll be trying to move away from. I think initially, because it is an established technology for export cables, for static sections of export cables, they may still be used, but certainly with the developments that are ongoing, I would imagine we will be looking at alternatives.
Yeah,
it's obviously it's very, very poor in fatigue anyway, so you wouldn't want to be using it for your dynamic cables typically.
yeah. Well, there is also some questions, I mean, I think are quite general. For example, about good semi-sub and spar design resulting in different dynamic cable configuration. I may answer, like for dynamic cable, depends. For sure, it will be different for the mooring and the anchors. And that's why we are treating it there separately.
Yeah, so the mooring systems will certainly be different depending on the floater design, but the implications of that for the cables are much less significant. It doesn't really because the cable is connecting to the floating device. It doesn't influence the floating device. The floating device influences it. For the cable configuration, it is much more a question of how much that device will move from its nominal position. So it's the excursion rather than the type that will dictate that.
Yeah. Then what else? There are some questions, I think that, for example, Ruben may ask or may answer, like, for example, this is quite directed, I think, for your concept, Ruben, because they are saying, what's the concept studied here differ from all of Ols and Star?
Well, both concepts are quite similar. Both are semi-submergible, and well, we are working in parallel in a very similar concept with 3 cones based on concrete and a central cones to support the tower of the wind turbine.
Yeah. There is, let me see, there are lots of questions just entering. Henrik, do you want, I see that you are aiming to answer some others.
Yeah, there was one question here which says, what is the water depth that we are looking at in COREWIND? So we have these 3 sites, and we are looking at a 100-meter water depth at the West of Barra site, a 200-meter water depth at the Canary Islands, and an 860-something water depth at the Morro Bay. So we try to cover water depths which are relevant and are also placed where we can see that there can be a future use for the technologies. And there was one more interesting question here. Currently, all platforms are significantly heavier than equivalent fixed structures, monopiles or jackets. So why is that so? And I think we have to bear in mind that floating support structures, they are used when the depths become too large for the bottom fixed. So for any depth, of course, you will always go with the cheapest possible structure. So if you can build a bottom fixed one which is less heavy, that will probably be the choice. But when you get to some depth, could be 60 meters, for example, then you will expect that the bottom fixed will become too heavy, and you will have a stronger feasibility for the floater. So that's the reason.
Then there is here quite an interesting question related to, I mean, from Álvaro Ponce de León, asking about the outputs, if they will be available and open for developers. The answer is that within the project we are planning to work or to open as much results as possible. Okay, so maybe not everything will be available, but this is for the sake of the, let's say, of the floating industry advance that we are aiming to make open even some data and some models and so on. Okay, so yes, this is one of the objective also of the project. And then someone was asking why we are focusing on that two technologies and not on other ones. Mainly, one of the decisions that we made was to focus on the concrete-based technologies. So even the spar that we are analyzing here in COREWIND are concrete-based. We believe that that concrete-based or hybrid steel plus concrete can really help on reducing rapidly the cost of floating wind. So this is one of the key decisions. Okay. What
There's
else?
been some questions about water depths and the use of cables in water depths. I have a question about how feasible do I think dynamic cables in sort of 1 kilometer water depths would be, and another question asking about dynamic cables already out in industry. So the technology in terms of the cable design is quite established and is used in oil and gas already, and there are dynamic cables obviously on all of the pilot projects, High Wind project, Kincardine, Windfloat. As for the kilometre water depth, there are technologies, as I say, under development, which will be intended for installation in much deeper waters. And I do see that there will be other innovations in terms of handling the cable, perhaps not all the way down to the seabed, which may also be a kind of cost optimization opportunity for dynamic cables for floating wind. In terms of the water depths that are used on the project, we've picked 3 sites which kind of show some indicative water depths, we think, for the sorts of developments that will be happening within the next sort of 10, 20 years. So I think we can perhaps direct to the right part of the COREWIND project website to answer some of those questions more generally if people are interested. Okay.
Yeah. There is also one question that is here. It's about the wind for control within the scope. The answer is yes. So we are also considering the control of the wind farm as a part of the scope of the project. And I think in early there were a question about if we are planning to make some tests of the cables and so on. And the answer is yes. There will be some lab testing for the mooring and also for some of the small scale prototypes and technologies on the cables within the wave tank on Cantabria. Okay, so we believe that with that we can really move forward. There were quite a general question also about if the cables will be AC or DC. And I mean, I think that Caroline can answer it, or maybe myself. So it's Caroline, if you want.
We're assuming AC for now.
Yeah.
Yeah. So yeah, we've assumed AC on the project. Obviously, there is a lot of discussion in the industry about DC, and I would say direct you to the research there. But no, for the purposes of this, we are looking at AC. There may be opportunities in the future for other developments, but AC for now.
Yeah. Also, that there were some question, I think, regarding the distances from shore for the the selection of the sites. Ruben, maybe you can answer that.
Well, now we have 3 scenarios. We have defined 3 different scenarios, working different depths from 100 to 800, and the distance to shore is around 50 kilometers, I think, no more in these scenarios.
Yeah. And what else? Well, there is lots of them. There were some questions regarding the LCOE and so on. So initially, some of the values that were provided as a general and a baseline, at least from the project, were coming from the IEA Task 26. Okay, that they made a report on the scenarios and how they foreseen the evolution of the cost. Okay, so we take that as a current reference and expected evolution of that. And then they are asking why Ruben was saying that Cobra is expecting that it will be 40 or 60 euros. Well, I think that at the end also one of the differences what you are expecting from your technology and what are your objectives, and then which is the, let's say, the global, because at the end when they are talking about LCOE, not only Cobra but in general, at least in the AEA, was all the technology. So you need to make an average. Of course, there is lots of variability related to that, but maybe there are some internal analysis on Cobra. So maybe Ruben, you can answer a bit more in detail why you are expecting,
No,
let's say by 2030, that values.
according to the last news that we have from the market, the sector is expecting a cost reduction and up to this rate in 2030. Okay, but it's a sectorial.
Yeah. Yeah, and then here there are some questions also about the LCOE and how the innovations will be evaluated for the LCOE. Within the project, there is one tool for LCOE evaluation, which is quite, let's say, specific, and it's quite easy to modify that for the sake of the innovation. So we can modify it, some function cost and technology and materials applied and so on, in order to make the scaling and the evaluation of that LCOE. So we are not using conventional tools for make that. So we believe that it will be enough for quantifying that innovations. Okay, let me. I'm for sure losing lots of questions. There is one quite general. I don't know if Sabina maybe can answer it or Caroline will know, but what are the policies or the incentive policies made in Scotland in order to really attract that amount of floating pilots compared to the rest of UK?
I think there's been just generally stronger government support from the Scottish Executive and the Scottish Parliament there than perhaps in the rest of the UK. And I think that there is a very strong renewable sector within Scotland, not just in floating offshore wind, but and the fixed bottom wind, but also wave and tidal developments. The Scottish coastline is particularly attractive for renewable energy generation, and I think that's part of the reason that Scotland has had such a springboard and is perhaps a little bit further ahead of the game than some other areas of the UK and in Europe.
Okay, so I would like just, I mean, there is lots of additional questions, but I think that time is running up. So I would like to add that, of course, the presentation and the recording of that will be available on WindEurope for the members, but we are also in discussion with them in order to see if we can share that slides also within the COREWIND project. Okay, so feel free to visit our website and see all the slides that we have made today. Okay, and then last but no least, also we were planning, or we were expecting to have a side event within the FOAT conference in Marseille. Okay, so we are expecting that at the end, of course, some of the partners within the project, if you want to discuss it, we will be there, okay, on September. So it's expected that the organization will be for that vote on the 7th to the 9th of September again in Marseille. They are expecting that date will be fine. Okay. So thank you for your time. Thank you for attendance. Hope you enjoyed the webinar. Okay.
Thank you very much. Bye.
Thank you.
Yeah, goodbye. Thanks.
Stay safe. Bye.